recording.
Yep,
Hello,
we're in.
everyone. Yes, we're recording. Hello, everyone, and welcome back to another MIPS workshop. Thank you all for attending. Today, I am very excited to have Alexei, who is going to talk to us all about Agora and AutoAgora, as you can see from the presentation slides. And with that, I will hand it straight to him to take us into the workshop.
Hi, thanks, Abel. Yeah, so we're going to talk about a little bit about Agora and then a little bit more about AutoAgora. It's all about, basically the theme is how to price the queries you're serving, right? Okay, so I'm going to introduce Agora first. It's going to be a short introduction. I'm not going to go too much in detail here because there's already some material out there, notably a workshop from Zach, who is the main developer of Agora. So yeah, I hope you'll get a chance to check that workshop out. In any case, the problem setting, we observe on real queries from the network that, you know, for some subgraphs, so in particular here we have Uniswap, the execution time of queries can span 3 orders of magnitude. So anything between 10 milliseconds all the way up to minutes, right? So another thing also is that we're seeing that queries are quite repetitive. So that means that for most of the queries you're receiving, you can take action and, you know, determine if you want to, you know, kick them out or, you know, price them according to their difficulty, right? I do hope, by the way, that you already know about GraphQL. I'm not gonna teach you about GraphQL in here, but there's a lot of material out there, right? In any case, in the context of the decentralized service, here are the components that are you know, playing a role in serving a query. So at the top, I'm gonna get the laser. Great. So at the top, we got the end user. The end user talks to the gateway. So the end user prepays for their queries with GRT on Polygon, or at least last time I checked, that's how it worked. And the end user is provided an endpoint to consume from their GRT money queries, right? The gateway will select an indexer for each query. Once again, I'm not going to go into detail, but basically the selection is a function of the economic security, which is how much the indexer has staked, I mean, how much the indexer has in delegation stake, and also how much is allocated to the particular subgraph that is being served. And other, you know, quality aspects, like how many failed queries there were in the past, and latency, right? And also the price of the query. So that's where it gets interesting. If you price the particular query that the end user sent too high, then there's going to be a higher chance that another indexer is going to be picked. In any case, so we got the end user send the GraphQL query to the gateway, and the gateway selects us, let's say. That query is going to go, so that query plus some payment data, cryptographic payment data that's generated by the gateway will go to the through the indexer service that the indexer is running. And the indexer service is tasked with interpreting the payment data and accepting the query and the payment, and verifying that the payment is correct, etc. And the indexer service then proxies that GraphQL query to the query node, which the software is called GraphNode, to actually process that query. And the GraphNode itself, of course, gets its data from a Postgres database that contains all the data from the subgraph. that's been indexed by the index node, etc. So here I'm only showing the flow of queries. I'm not showing all the rest of the components, indexer agent and the index nodes and your Ethereum nodes, etc. This is not here. I'm just showing the relevant beats, right? So an interesting aspect of all this is that the indexer service will also serve a cost model to the gateway, and that's how the gateway determined how expensive the query will be for a particular indexer. The gateway pulls the cost model from the indexer every about 30 seconds. So before you can receive a query and before you can the gateway can decide for a price, you have to supply a cost model. So those cost models are written in the Agora DSL. Here we have a little example of an Agora entry, and it looks very much like a GraphQL query, except that you define a price for that query shape, basically, right? So in particular here, we say that the base cost of that query is 0.0042 GRT plus 0.000038 times first. So if you, in that particular case, if the client asks for many items from the query response, we would charge more, right? And so that would apply for to an incoming query like such a query. And the charge price in that particular case would be 0.004314 GRT, right? So that's pretty much how it works. And that pricing is computed on the gateway prior to receiving the query. I invite you, I urge you, I would even say, to check out the Agora language workshop from Zach. That's the link, and you can snap the QR code. I'm also going to give a link to the presentation so that you can go back to this. So the overall flow, once again, I'm not going to go in details, but you can find some information in the READMEs of different pieces of software I'm going to mention here. But the manual flow to create your Agora models is that first you run your query node with graphlog query timing equals GQL. And that will make the query node spit out the query contents and the query execution times to std out. And then it's your job to capture the logs. Second step, you run those logs through QLog, which is under the Graph Protocol organization in GitHub for analysis. This tool will help you determine which are the most frequent query shapes, what are the execution times of those query shapes, etc. And it also will help you to generate JSON-L log files. Then what you can do from the information you got in step 2 from the analysis is that you can write by hand your Agora models for each of the subgraphs of interest. And fourth step, you can try out those Agora models using the JSON-L files that you generated with QLog. You can try them out with Agora itself. There's the Agora software also under the Graph Protocol organization. And that will basically estimate how much money you would have made if you had basically replace your history of past queries that you've served, and will help you determine how much money you would have made with that new cost model. So here's an example of a very small Agora model. We've got 2 entries and a default price. So here it's pretty straightforward to understand what's going on. And yeah, the default price is a catch-all. So that's, if the queries you're receiving are not matching those first 2, then it will be applied that default price. Once again, if you want to know more details, you can do way fancier things with Agora. Check out the Agora language workshop that I mentioned earlier. And in any case, after this, so you've got your Agora file, you can load it into your indexer stack to be served to the gateway using that command. So that command comes from the indexer CLI. And you run graph index for cost set model. You give the IPFS hash of the subgraph you want to apply this to and the file. And that will, after that, we'll start serving that model to the gateway for the gateway to price your queries. If you want to know more about that tool, though I would expect it has been mentioned already in other workshops, check out this link. It's a bit long, so we probably want to get to the presentation and go back to that page and get the link, and you'll get more information about what the graph indexer tool can do for you. So it's all nice, it's very powerful, but the problem is that it's hard to do and it's repetitive. You would have to run that loop I described here for every new subgraph that you're indexing, and ideally you would even redo the models for the subgraphs you were serving because the statistics of the queries you're receiving might change, etc. So some indexers just elect to put a default price, guesstimate, and then roll with it. But we're not very happy with this, and especially for MIPS, we really want you to optimize your revenue, right, and get as much revenue as possible. So for this, we created AutoAgora. AutoAgora is charged of automating pretty much every step of that process, and it's functionally it's split in two parts. It's split into relative cost discovery part, which helps you determine for each subgraph how different queries are cost in terms of your hardware relative to each other. Then in the second part, we're going to discuss how all of those prices are adjusted in real time to the current market conditions. Okay, so first of all, here's a diagram. Looks a little bit scary, but it's not too bad. And that's a diagram of part of the indexer stack and the AutoAgora components that you have to plug onto your indexer stack for it to work. So we still got our gateway, etc. The indexer service is wrapped in a container called AutoAgora indexer service, and its job is to automatically filter out the query timing logs, so the very ones that we were mentioning earlier, such that those are sent to a queue, and then those log lines are processed through the AutoAgora processor. What the AutoAgora processor is doing is extracting all the data from those log lines, such as the the query itself, the execution time, etc. That data is then saved into a new Postgres database that saves the query logs and the query skeletons. I'm going to come back to what that means. It's pretty much a log of all the queries you've served with how long that with their execution latencies. And AutoAgora then runs statistics from that database to determine which are the most frequent queries, and builds and updates the Agora cost models automatically. Those cost models are pushed to the indexer agent, just as the indexer CLI would do. And the indexer agent then takes care of pushing that to the database that the indexer service uses. And then the indexer service serves those AutoAgora generated cost models continuously to the gateway. Yeah, that's pretty much. So in green here, we got the original indexer components, and in blue are the AutoAgora added components, right? So I'm going to go into details for each step of the process. So, and in the Agora part, I discussed that the query execution times come from the query nodes. Here we are gathering that data from the indexer service. For the indexer service to give you that data, you have to set the environment variable query timing logs equal true, and you get those log entries. It's already in JSON format, and as you can see, you get your subgraph hash, get your query, as well as the query variables and the execution time in milliseconds. So that data goes into the AutoAgora processor, such that the query itself is extracted. So that's where it comes from. Yeah, from the queue. The query is extracted. The schema of the subgraph is retrieved from the indexer service, and that helps us normalize the query, because in GraphQL there's many ways of basically asking the same question, but at the end it's the same price for us. So we want to normalize all of that in our statistical data. The normalized queries are split into query skeletons, where we got only the shape of the query and no value in there. So for example, if you had a query that said, first 12, then first would be a variable in here, and 12 would go into the query logs as a separate variable. And the way we link those query skeletons to the query logs is by using a hash as the key, Blake2 hash, so a cryptographically strong hash, such that in case an attacker would want to mess with our pricing, they wouldn't be able to very easily figure out how to mangle their queries to confuse us, right? So yeah, all that gets fed into two tables, the query logs table, and the query, each log entry refers to a particular skeleton. I'm going to show you later how that looks in the tables. Here, it's extremely detailed, so I'm just going to fly through it. But pretty much, these are the steps of normalization and cleaning up of the queries to normalize them and separate the variables and the skeletons. Here's your supporting data to prove that we do need to normalize our queries. And here we have the frequency of the most queries. And before normalization, you can see that the frequencies are dropping much quicker than after normalization, because queries get grouped much more efficiently and much more tightly. So it does make a huge difference to normalize the queries. It's a very important step. And here it's just an example data that we got in our tables. So the logs table, we can see that refers to a subgraph, query hash, which refers to a particular query skeleton, timestamp of when we received that query, the execution time, and the variables to fill into the skeleton, such that we can completely rebuild the original query. And in the query skeletons table, we can see, so here, actually the first hash here corresponds to the first hash here, which is lucky. And you can see the normalized query, which is also very much compressed. All extra spaces and new lines, etc., are removed. So it's just a very compressed, very generic form of the query. So here to give an example, so that's basically kind of a compression technique, and it really works well, because sometimes those query skeletons are very large. So we can see that here we have 500,000. We've seen 500,000 queries, and we have only 64 skeletons. So that gives an idea of how repetitive those queries really are. And here our table, or query logs table, is using only 100 megabytes of data, so it's not very much. So yeah, so after that, we got the main part, the AutoAgora part that generates the models and just gets its data from the Postgres DB, determines what the most frequent query skeletons are, compute the average execution times for those skeletons, then create the Agora source file, and then injects it into the indexer agent. At the same time, AutoAgora determines which subgraph it has to generate Agora models for by asking the indexer agent what subgraphs are we actually allocated on right now. So it will not generate models for subgraphs that we are indexing off chain or something else. Only subgraphs that we're currently allocated on and thus serving right now. So using the indexer CLI, if you while AutoAgora is running, if you ask the indexer CLI what are the current cost models, that's what it would tell you. So that gives you an idea of what AutoAgora generated. And you can see that you get some comments here that just gives you a little bit of context data for you to double check, that those models are satisfactory. So it gives you the minimum, maximum time of execution that's been observed, the average and the standard deviation. Actually, here the standard deviation is quite large somehow. And you got your query skeleton and the price that was computed. So really what we call relative cost is that value here, right? So here we have a second entry, and it's a statistically cheaper query to execute. And we can see here that the relative cost is 44. So we got we got a good 2 orders of magnitude difference of cost between those two queries. Yeah, and we've got our default here still, because we still need a catch-all, right? And yeah, the interesting thing here is that we got a global cost multiplier. So all of those relative costs are multiplied by a global cost multiplier that is determined per subgraph, and that is fed as a variable to Agora. And so to determine what value should be fed in this, we have to compute absolute prices. So before we were caring about the cost of a query, and now we have to determine a price that is a function of that cost and the current market conditions, etc. So here's a rough visualization of how, at least from the indexer's perspective, how the query market looks like. As you increase your query price, you will see the queries, the query rate that you receive for that subgraph go down. So it will plateau at some level, and it will go down all the way to 0 if you price, if your prices are too expensive compared to the current market conditions. How it looks like in terms of revenue per second is like this. So of course, if you set your price to 0, you're going to get quite a bit of queries, but you multiply whatever by 0, you get 0, so you get no money. As you increase your price, your revenue will go up, and it will reach a maximum tipping point. After which, because you're pricing too high, you get less competitive and you receive less queries, so your query rate will sharply decline, and thus your revenue also. So once again, right, if your price is extremely high and you get no queries, once again, right, you multiply by 0, you get 0. And so the game here is to maximize our revenue, which is the average query price times the query rate that we're receiving. So for this, we decided to do some continuous reinforcement learning to continuously adjust a an action space that we've modeled with a Gaussian. So basically, we have just a Gaussian that's that's just determining the probability density for us to pick a particular price. And so we're sampling that Gaussian and changing our price multipliers constantly. And with this, we determine a reward function. That reward function is just our revenue. Sorry. And the reinforcement learning algorithm will tweak the standard deviation and the mean of that Gaussian such that we optimize our revenue. I'm going to show you after that a visual representation of what that means. It might seem a little bit abstract. In any case, the loop of the algorithm is we sample a price multiplier from the policy. So the policy is that Gaussian distribution over prices. We apply that price multiplier to Agora. We wait 1 minute. We measure. So 1 minute is because we have to wait for the gateway to apply that new price. Then we measure the number of queries per second we receive over a minute. And with that, we can compute the revenue rate we got over that minute. And then we can update the policy using the optimizer, using the revenue per second as reward. And we just repeat, and that will continuously move that Gaussian to follow the optimal revenue rate, which is the peak here, right? So that peak, just to give you more context, that peak will move around depending on how many indexers there are and how the consumers change their budgets, right? So we just want to move, we want to follow this guy whenever it moves. I invite you to watch that DevCon presentation from Thomas Cornuta, a colleague of mine. He actually presented yesterday at DevCon, and it's all about that algorithm. So yeah, check it out. In any case, here's a visual representation of what goes on. So what you can see at the top here is the red line is that Gaussian that we use to sample the prices. The x-axis is the prices, and the y-axis is the query rate in that top quadrant of the video. The gray line is the horizontal gray line is the simulated network query rate, and we add some noise to it because it's more realistic that way. And the vertical gray line is the budget limit that the consumer has set. So what you can see here is that we start over there with our Gaussian, and it will rapidly move towards the maximum limit, right? Trying to get as much money as possible. So I'm going to play it again. As we can see that Gaussian widens to figure out faster where that limit is, and then it converges down such that we can sample mainly, more tightly around the higher prices, right? So you can see the red dot here is just it samples quite a wide range of prices, and then it's getting tighter and tighter and tighter as it trains. So the reason why we've elected to use machine learning is that here, as you can see from very visually from that Gaussian, is that there's an equilibrium to play between what we call in reinforcement learning exploration and exploitation. If you want to explore more, you would widen that Gaussian. You can sample a wider range of prices, and you quickly see broadly what happens, depending on how you choose your prices. The problem, though, is that as you're doing that, you're learning a lot about the environment, but you are also getting less money, because to explore that environment, you will go into places where you get less money. Whereas when the Gaussian tightens, you're doing exploitation, which means that you have a quite high confidence in terms of where the optimal point is, and then you just stick there and then just, you know, get as much money as possible. I invite you to watch the DevCon presentation that I linked just before, because it has more experiments where you can see what happens if suddenly the price moves, and the Gaussian will just basically expand and then find the optimal point again, and what happens when there is multiple competing agents, etc. So I'm not going to go into those details because it was already presented by my colleague yesterday. Yeah. So here are the components that are involved with absolute price discovery. So there's a bit less components because we don't, for that price multiplier, we don't really care about what the contents of those queries I mean, we don't really care about the relative prices of queries, costs, sorry, but we care about basically shifting those prices to follow the market price. So the way we're doing it is by looking at the query metrics that are exposed by the indexer service. That's how we know how many queries were served in a chunk of time. And so, yeah, as we do this, AutoAgora will adjust that price multiplier variable in the Agora models and push it to indexer agent into the indexer services DB, and then indexer service will serve that to the gateway. And it just repeats in a much tighter loop, by the way, than the relative cost discovery. It will update pretty much every 2 minutes, if I remember well. So here are the metrics that we extract from AutoAgora. So AutoAgora sends some metrics to you, to the indexer's Prometheus, and we can see that. So here, that particular subgraph, I think, is UMA on Ethereum, and so we can see that the number of queries per second that we're serving is somewhat flat. You got to remember that the market and the number of queries that we're receiving varies, right? So it's not only a function of our prices, but it's also a function of demand, right? So that's why there's not a very much visible correlation between the queries per second and the prices we're sampling. In any case, we can see that the mean of the Gaussian fluctuates. So it starts pretty it's pretty high, and then it goes down a little bit to find that optimal point. We also see the standard deviation going down over time as confidence goes up about the market environment. We can see that also as a consequence in terms of the sampled prices that we're applying over time. You can see that it's extremely wide to start with as it's exploring and poking around to see what happens, and then it converges quite tightly. We can see our reward going up as expected. So that's the reward in that particular case is the price multiplier times queries per second. And we can also see that the GRT per second that we're making is going up over time. So it's a pretty good run here. So putting it all together, here are all the components. So you see the flow for the relative costing, which is going from gateway, receive query, goes through indexer service. Indexer service computes the execution time, goes into the logs, into the queue. That queue is consumed by the AutoAgora processors. That gets fed into the database that keeps a historical trace of all the queries we've served and what were their latencies. And that goes into AutoAgora to compute its statistics, to generate the relative cost models. It also gets the number of queries that are served from the query metrics, and generate those models. The Agora models, sorry, fits them into the indexer agent, which fits them into the indexer service DB, and then the indexer service serves those models to the gateway. So you got the full cycle here. There's some limitations with the current implementation. It's still a work in progress. But yeah, the modeling, the relative cost modeling is quite simplistic because it's just based on execution time. We could improve it with, for example, extracting special variables like first and skip, and inject those into the Agora models to have what happened there? Where was I? I was saying that, yeah, the modeling is somewhat basic for now, but it's still much better than having to do things by hand or not doing anything at all. But that could be improved over time. Also, for now, we're not computing execution time for multi-root queries. So what's a multi-root query? It's basically a GraphQL query that has 2 root nodes or more, right? That's a little bit tricky because Agora is costing those nodes separately, but in terms of execution time, we just get the overall execution time of the whole query with all the, including all the nodes in there. So yeah, that's a work in progress. And the problem with absolute costing is that it is a little bit slow. We're quite limited by the gateway's polling speed. So that's why you can see here, for example, in that run, it took, let's say about between 6 and 12 hours to get to a satisfactory convergence on the pricing model. Yeah, so that's it. So please check out the AutoAgora repo. And you also got a link to the presentation on the right side that will probably help you with getting all those links that I've shared here. Thank you.
Amazing. Thank you so much, Alexei. As we were going through the presentation, there were a few questions. So if you want to maybe scroll up into the chat and address some of the questions, that'll be a good idea.
Okay, let's see. Going up. Would those AutoAgora components be on our machines or in some cloud? It would be wherever your indexer stack runs, pretty much. It's tightly coupled to the indexer agent and the indexer service. So you would have to run it in situ.
Oh, yes, that was a question from me. I wanted to expand it a little bit. So I guess this stack is very computationally, requires a lot of computation power, or no?
No, not at all. That's the thing. It is very light, it turns out.
So the queries themselves would not be longer for our customers to get. It would be the same thing.
Yes. So first of all, yes, there is that flow, right? That sorry. Yeah. So you may think that there could be back pressure if, let's say, our AutoAgora processor is too slow. It would back up the indexer service standard output and could slow things down, but that's not the case. We have 2 levels of pressure reliefs, basically. So if the Rabbit MQ is if it fills up, it just throws away entries. And if there's any kind of back pressure in terms of our filtering software for the logs here, same thing. It just like throws away entries. So this was optimized for not impacting the system. We prefer throwing away log entries than slowing down the operations. It's a good question, though. Yeah.
In this whole architecture, I have a question about Postgres database. How much storage would it require, and can we delete some query logs that are older and I guess became irrelevant for newer versions subgraphs or newer time period?
Yeah. So yeah, we haven't done precise statistics, but in the one example I gave, for 500,000 queries, it was using about 100 megabytes of data. But yes, you could prune older entries, no problem. There is no automated process yet to do that, but there should be indeed.
And
yep.
how fast in terms of memory the model would be good enough to produce better results? So as far as I understand from the video, it takes some time, so it takes some queries just to learn the model, to teach the model.
Yeah, so the model itself, it is very compact, right? Because the only variables we're training are the standard deviation and the mean, right? So it's basically just two numbers, and then you multiply that by the number of subgraphs. But yeah, in terms of memory, it's very small. It's a few hundred megabytes for AutoAgora, a few hundred megabytes for AutoAgora processor. Yeah, it's very small. It's much less than the indexer service or even the indexer agent, as a matter of fact, much much smaller. We've developed everything in Python, so it's both, you know, easier to comprehend, and it's much lighter than the Node.js parts of the infrastructure.
Yeah, thank you for your answers and for your great presentation, great work.
Thank you.
I think it's going to be a nice tool.
There's still improvements to be made. So if you want to participate, if you want to check out the code, if you want to, you know, it's all open source. It's Apache 2. Okay, so next question. Do the drops to 0 mean that we serve some queries for free? No, we never serve queries for free. It is because, okay, let's go there and see. Drops to, yeah, there's some drops to 0 here. It's because we're sampling prices that are too high, and that means that we don't get queries for that amount of time. And that's because we're exploring the space. And so that information is basically a strong disincentive, right? It's a negative reward for the optimization algorithm. So it goes there, gets 0 queries, and then it learns it, and then it doesn't do it anymore, basically.
That was more a question about the video, because there were more drops to 0 in the late stages after the.
Yeah, that's interesting. Yeah, you're right. And so this could be seen as a prompt. So when it goes to 0, we're not serving queries. So that is actually, it's similar to the Grafana. It's because we're sampling over the price limit that the consumer set. See, when that point, the red disk flashes down there, it's right after the price limit that the consumer set. And so effectively here, we're not serving queries at all. In this particular simulation, because we have a single agent for the subgraph, it looks as if basically the query is never served, right? So the end user would be not getting data. From our experiments, as long as you have at least 2 indexers on a subgraph, that cannot happen. It's a mix of the fact that both agents are competing, so that limits basically how far up the agent will go. And also, because they're sampling randomly, there's a very little chance that they will both select a price that is over the consumer price. So if you're over, then the other guy takes the query, right? So that's the idea. In general, it's known that quality of service is poor when there is a single indexer on a subgraph. Ideally, you would get 3 indexers. Does it answer your question?
Yeah, it's answered completely. Yeah, thank you very much.
Sure. Okay, so will the recording and presentation be shared after the workshop? Yes. Yeah. Okay. Is there much of a response time penalty when attaching AutoAgora to our indexer stack? Has this been measured? So as I said, 0 penalty, because it is there's multiple buffers, right? So first there is the standard output buffer from the indexer service, because we're taking everything from the standard output of the logs, right, of indexer service. Then we got a program in Go that is filtering the logs. It is using internally buffers and queues, and it also has a pressure relief valve. So if the queues fill up, then entries are thrown away. Then the RabbitMQ queue is also has a pressure relief, also will throw away entries. So the penalty should be exactly 0. And if it's not 0, then write an issue and we'll try and fix it. But we have 3 layers of protection, so it should not impact at all. And that's it. I guess there's no more questions. Maybe some people want to ask with sound the questions instead of the chat. There's still time, I think, right? There's 10 minutes.
Correct. Yeah, we have 10 minutes. So feel free to ask more questions if you have any, guys.
Hello, can you hear me?
Yep. Yes.
Thank you for presentation, first of all. My question is, can we impact the price by hand? Maybe we could make some constant price or something, as you mentioned previously. It was possible, but what about automating system? Is it possible to set minimal price or something like that? Thank you.
Yeah. In this particular case, we haven't yet implemented minimum price, but that can be done. Yes. We are not expecting that a minimal price would be needed from our. We've studied the behavior of the gateways indexer selection algorithm, and we are. It is made in such a way, which you can see, by the way, from the Agora language presentation from Zach. But it's made in such a way that, for now at least, the market is made in such a way that there is no race to the bottom if there is multiple competing indexers. If it was a purely, let's call it linear market, you would expect indeed that as soon as you have more than one agent, they would just, like, try and get the queries and be cheaper than the other guy and then go down to 0. But that's not the case. Still, though, a minimum price should be implemented indeed. Yes. I guess we're good.
We have another question from OV.
Oh, the chat. Oh, sorry, I wasn't monitoring the chat.
No.
I switched from presentation to chat, and feels like we'll be at disadvantage if we're not running AutoAgora. Yes, and that's because, from my past experience, if you want to find the market price, if you want to do it by hand, you have to sit there for hours, and then it moves all the time. So that means you don't even get to sleep. Like every 30 minutes or 1 hour, like, okay, I'm going to check it again and adjust it. As you can see, actually, from too far back from here, once it's converged, you can see the mean is pretty much the market price, the optimal price. It's moving all the time. It's moving a little bit up, a little bit down, all the time. So we do have to do that by hand, which would be crazy. Okay, congrats. Which repo? Finish page, yes. I don't know why it was asked. Yep. Silly question. What if RabbitMQ goes down? If it goes down, what's expected is that the the AutoAgora indexer service, that wrapper should just throw away the data. Maybe I should test it just to be sure, but because I implemented this quite a while ago, but it should throw away the data. We can try all this mentioned on ongoing testnet, or you're encouraged to use it actually. If you want to, show that you can generate revenue on the testnet, the better. So yes, please use it and tell me if something is wrong. Can we A/B test AutoAgora? So by A/B test, I would think that you mean switching between a manual model and the AutoAgora and seeing which one is best. Is that what you mean, Anton?
Yeah, can it be even implemented into AutoAgora? So half of the traffic goes through AutoAgora and half of the traffic goes through normal pricing models as we have already, just to take a look.
Yeah, so that makes sense. The problem though is that we don't get to choose which price model is applied because it's the gateway. So you would have to change the price model that you've declared for the subgraph to the AutoAgora, to the gateway, sorry, and then it would just switch all traffic to that model. It basically all traffic goes through the model, right? That's the problem. So only solutions I could see is running two indexers, though it seems that it's in the rules of MIPS, that's not good, or manually turn it off and on. But yeah, there's not really a solution right now because the gateway is doing the pricing. It's not us. Does that make sense?
Yes, I see the obstacle there. That's why I wanted, maybe you knew the solution, how to make it better than just switching on, switching off.
Mm-hmm. Any other questions? So we're getting close to the end, but yeah, don't hesitate to just go to the repo and write issues. Yes, Daniel, you need some load for sure. That's actually one of the trickier problem we had with AutoAgora is how to make it not explode when there is no queries. Because basically, if there's no queries, the optimizer goes into extreme exploration because wherever it pokes at, there's nothing. So it goes wide, 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 and then get basically a number overflow and it explodes. So we do have a pullback force right now implemented that limits how far the policy can go, and it basically brings it back to the initial state if there's no queries. But yeah, it makes it kind of static. As team is running queries already, can we redirect this at some point into service? I don't quite understand that question. Still not sure what the question is. Is it a question about merging the AutoAgora into the indexer service or something like that?
Maybe as being partner of Daniel, working on the same thing, I can explain in real voice rather than chat that we were following the instructions of MIP guidelines to open the port for graph node. But now, as we saw in the announcement, it was like for graph node, graph queries, for queries node. So we're now wondering if we opened the exact port for this phase 0 of this MIP testnet. So there's still a question, and it ends tomorrow. So that I believe that was Daniel was asking about. Because the first there were instructions to open the graph node on port 8000, and later we found out that probably a query node was has to be opened instead.
So okay,
still
so
a question for us, so we're not sure if we're following all
so query node
needed or did something wrong.
Query node is the graph node. Basically, the graph node is tasked of two things, right? It indexes the data, so it basically loads subgraph data continuously into its database, and then it also serves GraphQL queries, so it's read-only from that database. The way it's recommended to run that stack is to separate the graph node into two parts. So you basically run graph node twice. And one instance of graph node is tasked on the indexing, and we call it index node, but it's still the graph node software. And the query node, which is also the graph node software, is turned into just a query serving mode. And they both talk to the same database. As to opening the query node, that's probably for debugging purposes, because in production, you don't want to open this because you're not going to get paid for queries that go directly to the graph node. Queries have to go through the indexer service for you to be paid, right? So this is just purely a debugging system, right? Yep.
Yes, that's absolutely clear for us that one endpoint is for serving paid queries and another for debugging purposes and accessing queries directly. But the question I think we still had is about this phase 0, which endpoint we had to open, because it wasn't very clear if we need to open the debugging endpoint or the paid one.
So basically, AutoAgora will only care about the indexer service, if that's also the question, because that's the payment layer. Whatever goes through graph node, we're ignoring completely. And that has also advantages. The advantage is that we can rerun queries if we wanted to, and they're not going to affect our data sets. Because we would bypass the indexer service. So that's the very reason why we're getting that data from the indexer service. But yeah, in terms of what should be open or not, I'm not quite aware. You'd have to ask other people that are managing MIPs. But in any case, AutoAgora will work because it's internal. It's inside your infrastructure, so you don't have to open any port to the outside for AutoAgora to work, because it's going to run in your cluster, right?
Yeah, that's very clear. Thanks.
Yep. So under stress with an enormous amount of queries, would Agora help to serve them better, or on the opposite, make things worse due to additional computations? I mean, it depends what machine you're running on, I guess. The AutoAgora processor could end up using quite a bit of resources, but you would need a huge amount of queries. We've tested a single AutoAgora processor can go through 10, 15 queries per second, no problem. I don't remember which limits we set in our Kubernetes cluster, but they're very small. I think it's 1 CPU each and 500 megs of RAM. But even that amount of RAM was overkill. We can lower it. So yeah, yeah, I hope that answers the question. But in our particular case, we're running in Google Cloud. So actually, you can see in the diagram that here the reason why I put those stacked rectangles is that you can run as many AutoAgora processors as you want. So if it's not going fast enough, so first of all, if you don't want to have impact on your system, just run the one. If it can't take all the queries, then some are going to be thrown away. And that way you limit your impact to 500 megs of RAM and one CPU, right? If you don't want to throw away data for the training, then run multiple AutoAgora processors. If you can scale, if you can afford to scale. In our case, for our setup, we can afford to scale. It's just going to ask for more VMs from Google Cloud, and it's okay. It's up to you, though. But once again, the impact of all the AutoAgora stack is small compared to the query node and the indexer service and all that. So it's about maybe an order of magnitude less, right? So, okay, according to Cohen, AutoAgora and MIPS phase 0 are not compatible. And that I would guess is because queries are not going through the indexer service yet. I don't know. Correct. Okay, great. So yeah, there you go. Now I understand the nature of the whole problem. But yeah, eventually the load is gonna go through the indexer service, right? You gotta test this because there's a lot more involved with the indexer service. Basically, whenever you have the indexer service on, then you also have the proper, the actual gateway code running on the other side, and there's like payment channels and etc. So yeah, eventually that's going to be turned on because there's a lot of components there that have to be tested, etc. At least I would expect. Maybe Ford would know this. Because indeed, if the indexer service is never ever used, that means that your revenue will never ever be taken into account in terms of the your performance, and AutoAgora is useless. So that would be sad.
Oh, indexer service will definitely be used. Yeah, phase 0 is really just mostly to get indexers that are not that are new to the systems familiar, so they can only focus on the graph node first, and then in the next mission we'll be adding the other components.
Okay, great. That makes a lot of sense. Cool, super clear now. Thanks. Okay, gonna put back the QR codes just in case. Any more questions?
All right. Well, if there aren't any more questions, then I'll take this opportunity to wrap up today's conversation. Thank you, Alexei, for presenting. This was highly informative, and I hope it was the same for everyone here too. As we've established throughout the presentation, this will be recorded and put onto YouTube. There'll be a link to the MIPS playlist where it will be posted, and also there is a link to the presentation in the chat, and that will also be shared after as well. Thank you all, and we look forward to seeing you at the next MIPS workshop, which will be happening next week, Tuesday at 5 p.m. UTC. Take care, everyone. Bye-bye.
Bye.